Hello again, everybody. In the previous video, I introduced the concept of engineering and true stress strain curves and their underpinning theory. In today's video, I'm going to show how to compute these curves and by using a simple Python script. But I would like to point out that this is not a tutorial about how to use Python. And therefore, you need to be already familiar with the programming language. If it's so, let's get started. When you perform the tensile test, the results are typically saved in an Excel file, which will look like this. As initial data, you will have the force, the displacement, the initial length of your specimen, and also the initial diameter. At the end of this video, we would like to obtain something like this. So where you can see the engineering and true stress strain curves, and we also would like to identify some points of interest from an engineering perspective. Okay, now I'm going to open a Python script that I've already made for you, and I will take you through it. So the very first step is to import relevant modules. In this case, I imported matplotlib to make our plots, and then NumPy to perform some mathematical calculations, and also open PyExcel to read or save or upload your Excel file. And the very first task is to load the Excel file. Make sure that you identify the location where your Excel file is. And then we are going to read the very first spreadsheet of this workbook. And the next step is to work with our raw data. In particular, we are going to store this data, which is basically the displacement, force, initial diameter, and initial length, into arrays by using for loops here. So we got our raw data, and we can use it. The very first step here is to compute the initial area or initial cross-sectional area of your specimen by making use of the initial diameter. And in this calculation, we assume our sample is cylindrical. And then we can kick off computing the engineering stress strain curve, in particular, engineering stress and the engineering strain. The engineering stress is given by the force divided by the initial area of your specimen, whereas the engineering strain is given by the displacement divided by the initial length. And we are going to plot, we use these two information to plot the graph. And the graph will look like this. So once obtained the engineering stress strain curve, we would like to identify some points of interest. One of these candidates can be the ultimate strength, which is indicated with sigma u here, and basically is the maximum engineering stress a material or sample can sustain before fracture. And then we would like to plot this point onto the curve. And we need the x-coordinate here, basically indicated by the engineering strain, or actually the ultimate engineering strain. So basically calculated at this point, at the maximum point. And we can make use of this expression here to identify it. And then clearly we're going to use as y coordinate the sigma u, and the result will be something like this. And then we have here the point identifying the maximum of this curve. So the next point of interest is definitely the failure strength of failure and also failure strain. In order to compute the failure strength indicated with sigma f here, we are going to pick the very last value of the stress. And in Python, this is made by using this kind of structure or expression, brackets and -1. So we pick the very last value of the stress, and we do this for the strain. And then we are going to use these two values to compute or to plot our failure point, which will be looking like this. And it's going to indicate the failure point of our specimen. Now we are going to identify the last point of interest, which is the yield point. This is the most difficult one to identify. Since we are dealing with a metal, we can make use of a conventional method called 0.2% strain offset. But be careful here, because this method may not be applicable to polymers. what we would like to do here is to draw a parallel line to the straight line of our graph, which basically indicates the elastic domain. So this new line will start from 0.2% strain or 0.002 strain. To do so, we calculate the strain offset by adding 0.002 to the strain. And then we are going to calculate the Young's modulus, which is basically the slope of the straight line. The slope is given by delta sigma divided by delta epsilon, calculated at 2 chosen points on the straight line. And we would like this parallel line to intersect the curve at some point, which will be our yield point. The parallel line will start at the offset and will extend beyond the engineering curve. And to do so, the y-coordinate will be expressed as the product between the Young's modulus and the engineering strain. And then finally, we are going to obtain something like this. And by hovering the mouse pointer onto this intersection point, we can immediately read the value of the yield strain, which is basically 0.0057, and the yield strength, which is roughly 743 or 42 megapascals. Okay, so we can conclude this video by calculating the true strain and true stress. So the true strain can be easily computed by taking the logarithm, the natural logarithm of 1 plus the engineering strain, as written here, whereas the true stress is given by the product between the engineering stress and 1 plus the engineering strain. And we can plot these values here, and then we are going to obtain our final plot with all the points of interest, and we can also compare the true stress strain curve versus or against the engineering stress strain curve and see the difference. I hope you guys found this video useful and instructive, and I'm looking forward to see you in the next one. Bye for now.